everyone. Okay, so I'm gonna go over this alternate assignment. It is 8 pages long, but as you notice, there's a lot of writing in it and everything. It just has like notes and everything. And there is one more extra topic in there that I did want to cover. It's the repeated nearest neighbor algorithm. I thought since we might as well do this. Again, these I'll go over every answer to this as we do this together. And if you have any questions, I'm gonna set up some office hours for you. But what you need to do is make sure you complete every page of this, scan it in and turn it in to me, and then email it to me or send it to me uh, on Edmodo. I'd rather actually you email it to me so at least I have it and take a look at it. But anyways, so when we're trying to do Hamiltonian circuits and solving the traveling salesman problem through that, one of the ways that we can do it and the one to get the most optimal solution is through the brute force algorithm. It's also known as an exhaustive search strategy because you go through every possible option and it's guaranteed to produce the best solution because you find the one that costs the least amount. And so we're going to start with that one. And then we're going to talk about the other algorithms and when it would be more optimal to use those um, in regards to solving these algorithms and coming up with the best, most useful path. Okay, so let me do this real quick. I'm trying to, no, it's not working. Awesome. Okay. I just want to make sure my pen is as small as it can be when I'm doing this. So the first thing you want to do is make a list of all the possible Hamiltonian circuits for the graph. And in order to do that, to know the number of them, as you need to do is you take n is equal to the number of vertices in the graph. And so our possible number of Hamiltonian circuits is n minus 1 factorial. And that includes both the circuit and the mirror image of that circuit. So what you guys might remember is that we did n minus 1 factorial divided by 2 because those are the original ones, but we're just going to use this n minus 1 factorial to get you through this, okay? So, oh, there we go. That's what I wanted. Okay. So I wanted to go ahead and let me put this up really quick. I'm sorry, guys. There we go. All right. So what you're going to do is come up with all the possible lists. And what we did is we did a tree diagram, and then you choose an optimal circuit, right? The one that gave you the lowest amount. So for this one, what's nice is that we came up with these. We created a table, which I think is also a good possibility for it. You want to first start out with, um, because there's 4 vertices, we're going to do, to come up with a number, we're going to do 4 minus 1 factorial. So that's 3 times 2 times 1. So there's going to be 6 possible circuits. Okay? So there's 6 possible circuits. That includes these and their mirror image. Okay? So the first one that I came up was A, C, D, B, A. And the mirror image of that is just this in reverse. So it's A, B, D, C, A. Remember, for a Hamiltonian circuit, you have to reach every vertex, but not necessarily every path in between, okay? and you have to come back to the original starting vertex. So we're going to start, we started in town A. So for that one, went from A to C, and A to C is 70. And then we went C to D. C to D is 50. And then D to B, which is 10. And B to A, which again is 20. And that gives me 150. All right. Now what about this one? We can do A, D, C, B, A. And that one is A, B, C, D, A in reverse. And that one we came up from A to D, which is 30, and D to C, which is 50, and C to B, which is 15, and B to A, which is 20, which gives me 115. All right. Then there's one more, which is A, C, B, D, A, or we could do A, D, B, C, A. And that path gives us 70 plus 15 plus 10 plus 30, which gives me 125. Now, as we can see, this is my optimal solution right here, okay? This 115. So this is A, D, C, B, A, or A, B, C, D, A. And the distance of that route is 115. Okay, so that's our optimal solution. So let's try another one with 4 vertices, which is the next one here. A delivery truck starts with the warehouse at point A and must deliver furniture to B, C, and D. How many possible Hamiltonian circuits are including the mirror images are there in this problem? Well, there's 4 vertices, so I do 4 minus 1 factorial, so that's 3 times 2 times 1, which is again 6. Okay, so from here we can do A, B, C, D, A, or A, C, D, B, A, or A, D, B, C, A. So this is A, D, C, B, A. And then this is A, B, D, C, A. And then this one is A, C, B, D, A. And then we come up with the links to those. So from A to B is 38. B to C is 22. And C to D is 8. Plus, and then finally to 12. So that's going to give me a distance of 80. And then we just do the other ones exactly the same, following the route. We have 18 plus 8 plus 10 plus 38. So this one gave me 74, so that's a little bit better. Now let's try this last one. That's 12 plus 10 plus 22 plus 18. And that gives me 62. So the optimal route is the last one that we came up with, which is ADB, BCA, or ACBDA. And the, let me erase that. Okay, back to the And the distance for that one is 62. Okay, so this actually makes a lot of sense when we're doing a lot or a smaller number of vertices. We can come up with the exact same solution. And in modern day, we have computers that do this all the time for us. So that's what basically what a GPS does. Okay, it comes up with all the different routes that you can go, and they usually choose the one that is the shortest, based on your preferences, of course. So on to the next page, we have 5 vertices. So watch what happens when we have one more vertice. We have 5 minus 1 factorial, so that's 4 times 3 times 2 times 1, which now gives us 24 possible solutions, which is a lot. But what's nice here is that they came up with all the different possibilities. So all we have to do is come up with the costs of those. And so I'm going to have you guys just pause the video here for a minute instead of you guys watching me come up with all the different lengths. I want you to go ahead and try to go through these and calculate them and then come back and check. All right, so give it a pause. Okay, so hopefully you got that filled in and we're able to realize that here is your nice little optimal solution right here, which is EB A DCE, or the mirror image of that, which is ECDA BE. All right, and that travel time is 76. Okay, so what we do here is what about when we're trying to find a ultimate solution here? How many possible Hamiltonian circuits? So we have 4 possible vertices. So that's 4 minus 1 factorial, which is again 3 times 2 times 1, which is 6. So in order to use the brute force algorithm to find an optimal route for the tour, we're going to create our own table to solve the problem. So what I'm going to kind of do is just do that one is, so the first one we're going to do is Louisville to Nashville, right? We're going to use this Louisville to Nashville, right? So we can't use any of these. And then from Nashville, I have to look, I'm not going back to Louisville. I have an option of these too. So I have 299 right here. So I have Louisville to Nashville to St. Louis. So then I don't have St. Louis as an option again. And from St. Louis, I can either go to Pittsburgh or Louisville, but I have to go to Pittsburgh, right? So I'm going to go to Pittsburgh. All right. And then from Louisville, I'm sorry, from Pittsburgh, I'm going to go back to Louisville. So that's 388. Okay. So that ends up being 1,443. So that's actually a different way to do it instead of coming up with every possible algorithm, which is kind of nice. All right, so that's in general your brute force algorithm, which is what we've already gone through, so it should be pretty familiar to you. But I wanted to give you guys some options so you can see the possible outcomes for that. The next thing that we're going to talk about is the nearest neighbor algorithm, which is also known as the go cheap strategy. So what happens is you're going to, it's an approximate algorithm. It's going to produce a solution that is efficient but not necessarily optimal. It does not always come out as the best solution, okay? Because it's using a method, but it's not necessarily the only option. Okay, so what you're going to do is start at a designated vertex, and that designated vertex is going to be one of the determining factors on whether or not you're using the most optimal solution. And then from there, you choose the cheapest one from each one and repeat until you go to all vertices. So let's take a look at what we did here for this one. When we did the brute force algorithm, we got this, A, D, C, B, A. But if we're using the nearest neighbor, okay, so the first thing, I start at A, and I'm going to go to B. All right, so A to B is 20. So that's A and then B. And then I want to take the cheapest one from here. So I'm going to go to D, right? So I go A, B, D, and then I have to go to C, and then I go to A, B, D, C, A. Okay, so it's a little bit different than our optimal solution. So we went from A to B to D to C to A, and then the mirror image of that is A, C, D, B, A. And the distance for these routes, let's go ahead and add them up. I'm going to take my calculator. I have 20 plus 10 is 30, plus 70 is 100, so it's going to be 150. Okay, now is that the optimal? No, it's not. These are not optimal routes, but they are close, but not necessarily. Now let's do the same thing that we did. We're using, if you notice, we're using examples 1 and 2 from the brute force algorithm. So let's try these, okay? So we're going to start again at A, and we're going to use the nearest neighbor problem, or the nearest neighbor algorithm. So we start from A, we have 3 possible vertices. We're going to go from A to D. So remember, for the brute force, we used this one, which had a total time of 62 minutes. So I went from A to D, and then from there I went D to C, which is C, and then I went back to B because I can't create a circuit before it's too early, and then I went to A again. So I went A, D, C, B, A, or the mirror image of that, which is A, B, C, D, A. Now let's talk about what the length is for these routes. So I went from A to B, right, which is 12, plus 8, which is 20, plus 22 is 42, plus 38. So 42 plus 38 is 80. So this route is 80. And keep in mind, that's not an optimal route, okay? These are not optimal routes, no. So compare the solutions between the brute force and nearest neighbor. When you have a small number of vertices, is it better to do the brute force? And yes, it is. Brute force is better for a small number of vertices. So I would say that's 4 or less. Okay, so let's go back. Let's go and look at the big one that we were given, which is right here. We have, it's the same as example 3 from brute force. So let's go to that one. Okay, we have the same distances and everything. So again, we're going to start from A, and we're going to use the nearest neighbor algorithm. So we went from A, We start at A, and the cheapest one is either 30, 12, 40, or 15. So we're going to go to 12. So we went from A to D. Or do we start at E? Oh, we want to start at E. I apologize. Hold on, let me erase that. Okay, I apologize. I knew something looked funny. So we're going to start at E. So we're going to either go from E to D, or E to C, or E to B, or E to A. Well, the cheapest one is this 13. So we're going to go E to B. All right. Then from here we have 14, 11, 15. So we're going to go this 11. So we went from E to B to D. And then we can either go here, which we don't want to do, and 13 and 12. So we're going to go to A. E, B, D, A. And then we have to go to C. And then we go to E. Okay? All right. So using the nearest neighbor algorithm, we came up with E, B, D, A, C, E. The other way is E, C, A, D, B, E, and the length of this route is 89. Now, if you notice, it's not as small, and if you look, we had one. That one's also on our list in the brute force algorithm on the previous pages. So that came up with 89. So it's not the same, but it's pretty darn close. And if you look up on your table that you created on exercise 3 doing the brute force algorithm, that is actually the third smallest. So there's an 86 and an 89. So under those, that 76. So are they optimal routes? No, they're not optimal routes, but they are reasonably close. Yes. And instead of doing 24 sums or 24 different paths, it's better to use the nearest neighbor algorithm because it's less time consuming and still pretty optimal, but not consume less time. Oh, oops, I should have done consuming. Oopsies. It's pretty optimal, but not perfect. Okay. So what about this guy right here? A country western band in Nashville is planning a 7-city tour. The mileage chart is shown for the 7 cities. Okay. So use the nearest neighbor algorithm to find a route. So we're going to start at Boston. Okay. So we're going to go from Boston. So we start here. And the nearest neighbor would be right here to Pittsburgh. Okay. So we went from Boston to Pittsburgh. Okay. So here we can't go from to Pittsburgh any other place. Okay. So, and we're going to cross these out as well. All right. Now, from Pittsburgh, I can go to any of these. So what's my lowest one? My lowest one is right here to Louisville. So we're going to go from Boston to Pittsburgh to Louisville. So I can't do Louisville any other place. Okay, so now from Louisville, I have all these places to go, but the cheapest place from Louisville is Nashville. So I'm going to go ahead and get rid of Nashville as far as an option. So Nashville, I can go to all these places. So let's see which one's cheaper. That would be $660, right? So we're going to go ahead and get rid of these guys. And we're going to Dallas. All right. Then from Dallas, I have the option, I don't want to go back to Boston. I want to go to either Houston or St. Louis. So I'm going to go to Houston. All right, so Houston. So then from Houston, I can go, I don't want to go back to St. Louis, right? Because we already did say, oh, wait. What did I do? 1, 2, 3, 4, 5. Oh, wait, I have one more to do. Houston. Okay, so from Houston, yes. So from Houston, I don't want to go back to Boston, so I want to go to St. Louis. So I go to St. Louis, boom, boom, boom. And from St. Louis, I go back to Boston. All right. So using the nearest neighbor algorithm, so we're going to go BPLNDHS, or the mirror image of that is SHDNLPB. And the sum of those routes, let's go ahead and count those, let's put those together. I got 1141 plus 660 plus 243 plus 388 plus 168 plus 561 plus 779. And that one is 3,940. Okay, so that is using the nearest neighbor algorithm for that. Now, the next thing that we're going to do is the repetitive nearest neighbor algorithm. So I want to give you guys a chance to work on those, but this should get you through the first 4 pages. And then I'll post another video going through the last 4 pages of this. I hope it's helpful. I hope you guys are doing okay. And thanks again for watching this and trying to improve your grades.